Thanks very much for the invitation, and thanks for everyone's listening to my talk. Today I will introduce the implicit regularization of SGD. Okay, and I will use the implicit regularization of SGD to explain some phenomena observed in large language model training. For example, the double descent phenomena and the emergence phenomena. And then I will then introduce a new algorithm for training large language model. So let me first briefly introduce my research. So currently, I mainly focus on three parts. The first part is about the optimization, and I am interested in design faster algorithm, and also interested in proposing some improved analysis. The second part is about generalization. However, different from previous generalization theory, I'm more interested in optimization-based generalization. So in traditional statistical learning theory, the generalization is based on an argument called uniform convergence. However, for large language model, so the member of parameter is often much larger than the number of samples. So it's very strange why we can also have a good generalization performance. And I think the reason is that we use some specific algorithm. So the algorithm will impose some regularization and control the model's capacity. In this way, we can obtain a good generalization performance. And my last research aspect is about causal discovery. So in generalization theory, our goal is to learn the data's association. In real world problems, maybe causal association is not enough, and we need causal association. And I also design models to learn causal association. Okay, but and in today's talk, I will mainly introduce my research based on my research in optimization-based generalization. And I will mainly focus on linear model, because linear model is much easier for our analysis. Sorry. Oh. Okay. So what is the implicit regularization? As I have talked about, so in previous statistical learning theory, so the model's generalization preference is based on the model's capacity. However, for our parameterized models, the member of parameter parameter is often much larger than the number of training samples. So the reason why we can have a good generalization is because the algorithm controls the model's capacity. So this is often called as implicit regularization. The algorithm guides the model to converge to some solutions that has some special property. So we don't need explicit regularization. The algorithm will impose some regularization, and we can have some good generalization performance. For example, in logistic regression, we already know that the gradient descent algorithm initialized at the 0 will converge to a max margin solution. So it means that if we train logistic regression by gradient descent, we actually will obtain a solution that is same as the solution solved by a SVM. Okay, and also for linear regression, if the parameter is initialized at 0, then gradient descent will converge to a minimal norm solution. And in recent years, many research have established some result showing that the minimum solution will have a good generalization.
Sorry, can I ask a question?
Yeah.
So if we initialize not in 0, but maybe in some like random point, will we converge to the solution that is the closest to this point where we initialized? Or it's like a magic number 0? Why it happens?
Sorry, you mean for logistic regression or linear?
Oh, okay, just linear regression maybe.
Okay. So for logistic regression, so if you don't have regularizer, the optimal solution is at infinite. Okay, but you can scale it. You can scale it to norm around 1. Then this solution is same as the is the max margin solution. Okay. So you can interrupt me if you have any questions, and you can also type on the Windows, and if I saw it, I would respond to you. Okay. And I will introduce the. Today I will mainly focus on the implicit regularization of SGD, not gradient descent. And I will mainly introduce our result on linear model, because linear model is easy, and I think everyone can understand it. Okay. So our first work is about the learning curves of stochastic gradient descent in color regression. So I will first introduce some background. So in traditional statistics, so with the number of parameter growth increase, and the test performance is usually behaves as a U shape. Like this. Okay, so if the number of parameters is very small, then we are so the learning is often called as underfitting, and when the parameters is the number of parameters is large, we often call it as overfit the data. However, in recent empirical studies, some researchers have found that when the parameter when the member of the parameter further increases, and we will encounter a second phase called the double descent phase. And in this phase, the test performance will continuously to increase like this. Okay. And later, some research also found the phenomenon called multiple descent, shown in the right figures. So here, he treat the number of training data as a polynomial factor of the input dimension. So with the gamma increase, the learning the learning are composed of many phases, and so it's called as multiple descent. Okay. So in traditional optimization, okay, we often obtain a convergence rate like 1 over square root of k. So, however, for the linear regression for this machine learning problems, the convergence speed or convergence rate varies across the learning process. Okay, it has two phase or multiple phase. So I want to explain why we will have this phenomenon when we train a machine learning model. Oh, sorry. Okay. So we consider a color regression problem, and the color is choosing as the new attention color of ReLU network, and we also have some basic assumption on the target function, and it's called source condition. This assumption is standard in color regression. So when S is 1, this assumption is like it is often used in color ridge regression as like the two norm of the weight is bounded by 1. Okay. And we will study the stochastic descent algorithm. So for stochastic gradient algorithm, and at each iteration, we will choose a random sample and do the stochastic gradient descent. And the difference in our analysis is the step size schedule. Okay. So we consider the schedule as so the step size decays exponentially. So given the total of n iteration, so the step size is like we first fix the step size at some iteration, and then divide by the step size by 2. Okay, and then fix this step size for certain iterations. And we also consider another setting. So in this setting, we will choose a constant step size. However, the output is an average of the previous iterations. And okay, we first show the result, and I will then explain why we can obtain this result. Okay. Firstly, we show that we can prove that for any gamma, Okay, for any gamma treating as a constant, then the SGD can achieve the optimal. The optimal means that we can design some lower bounds showing that any algorithm any algorithm at most can behave like this. Okay. And when S is large, so color ridge regression is not optimal. So the green line is the color ridge regression. Okay, and okay, these two lines are the SGD rate and the min-max rate. Okay, and okay, and the left figures describe the learning rate or the learning speed. We can see that for some point the convergence rate is so 1 over square of t. Okay, 1 over square of n, like SGD 1 over in SGD is also 1 over square of t. However, for many other points, the convergence rate is faster. Okay, it's faster than 1 over square of n. And and for color ridge regression, it's a lot optimal. Okay, it's a lot optimal. And then I will introduce so how we can have this how we obtain this result. So as the problem is in linear regression, so the learning dynamic is linear dynamics. Okay, for the SGD, and so we can separate the access risk by two terms. The first term is the bias term, and the second is the variance term. So what is the bias term? So we can imagine that the gradient, the stochastic gradient is stochastic gradient involves involves in its population level. It means that, for example, we use a very large step size, and so we don't have noise during the iterate. Okay, and the variance then reflect the variance then includes the noise effect. Okay, and so for color regression, the number of parameter is very large. So actually it's infinite. So, but however, when we train color regression by SGD, we also have a good generalization performance. So, however, we don't impose any regularizers. So why we can have a good generalization? The reason is the implicit regularization of SGD. So let us consider the bias term. So the sigma is the big sigma is the covariance matrix of the color. So so if the mu1 and mu k is the eigenvalue of big sigma. Okay, mu1 to mu k and is the eigenvalue of sigma, and it decreases. Okay. Then so if given an iteration member such as t, so if we know that if t is larger than 1 over 1 over eta 0 multiply mu k, then this term is nearly 0. Okay. However,
Okay. However, if t is smaller than 1 over eta 0 multiply certain mu, like for example mu j, then this term is still 1. Okay. Okay. So we have that if we have some point k star, so if I is smaller than k star, then the bias term is nearly 0. Okay. And when I is larger than k star, then the weight is nearly that does not change. So it's approximate W0. Okay. So for SGD algorithm, it only learns the first top k eigendirections. Okay. SGD only learns the first top k directions, and for the rest directions, is nearly the parameter is nearly at its initial value. Okay. So the SGD can be regarded as imposing some regularizations and control the weight to 0. Okay. At these directions. Okay.
So can I ask a question?
Yes.
So basically, K star depends on our initial learning rate at 0.
You mean K star is yeah. The algorithm is initial. Yeah. The algorithm is initial at 0. Yeah.
So if we take a small enough at 0, then we won't obtain any K star or what?
Sorry.
So basically, if all mu k are like less than 0.
You mean mu? Yeah, mu.
So,
You mean
So I don't understand why K star always exists.
You mean this is near 0? Why this is why
yeah. So
is near 0?
that's So why there always exists K star that like contains this ln n and n at 0? Why it's always like that?
You mean why mu is near 0?
No, what if all mu's are like on the left from this equation with n's?
You mean this or this?
Yeah.
This one or this one?
No. So if all mu's are on the left from ln n divided by n at 0.
So I first explain. So when mu is near 0, this is because we work on color regression. So for most color regression, the eigenvalue, so the trace of big sigma is bounded. Then we always have that the mu will most of the mu will be near 0. Okay, the trace sigma is often bounded. Okay, for color regression. For color regression, the trace of big sigma is bounded. Then so it indicates that the sigma of the sum of mu k is bounded. So for rest of mu k will so like k to 0 to infinite. So for most UK, it will very near 0. Okay. Then if mu k is near 0 and we run the algorithm by gradient descent, the dynamic is like this. Okay, it's linear. It's linear. It's converted to the optimal solution exponentially. However, the rate depends on the depends on the convergence rate. Okay. So if mu is very, very small, then the W will be 0. Okay. Where there is an initial value. And we assume that its initial is at 0. We assume that we initial W at 0. Okay.
Okay, now I understand. So if all mu's are like near 0, then we already in the good point.
Yeah,
so
yeah.
We don't need any optimization.
Yeah. So
and also now
I love your question. You also you maybe also curious about why the W star is near 0. Maybe you are so
okay.
This is an assumption like okay, like this. Okay. So you always have, for example, when S equals to 1 in closed regression, it means it indicates that the tuner of W is bounded by 1. Okay. So for this under this assumption, you can know that most of W will near 0 because all W, the square norm of W is bounded by 1. Okay. 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 So if W is initial at 0, so the after training, most of W is also nearly 0, and we can have a good generalization performance. Okay. Okay. Do you have
Okay.
question?
Maybe the last question. These mu's are like eigenvalues.
Yeah.
Of the sigma, but
yeah.
In which point? In the initial point?
No,
the W0?
for linear regression, the sigma is fixed. Okay. For linear regression,
okay.
it's induced by the curve. Okay. Okay.
Okay. Yeah. Thank you.
Okay. Okay. And then and then I will explain why we have the I will have the why the convergence rate has multiple phase. Okay, why the convergence rate have multiple phase? The reason is very simple. So because it depends on mu k, okay, or the lambda k. It's same. Okay, it's the same. It's the same. So we can calculate out the mu k. So the mu0 is around 1. However, and then we have d mu k at the scale 1 over d. Okay, then we have square of d mu k at the scale 1 over square of d. Okay. So since the SGD will learn the coordinates, learn these coordinates gradually, and so the convergence rate becomes multi-phase. We first learn the lambda 1, and then we learn the last d eigenvalues, and then we learn the last the square of d eigenvalues. So the rate has a multiple phase. Okay. Okay. It's just because of the eigenvalue. Okay. Okay. The eigenvalue does not decay as a polynomial like 1 over square t or 1 over square k like this. Oh, it's 1. The first is 1, and the last d is at 1 over d, and the last square of d is at 1 over square of d. Okay, like this. Okay. Okay. And then I will introduce our second work. Okay. This work we consider the generalization performance of SGD under the covariance shift setting. Okay. So for large language model training, so we cares of in distribution generalization, but we also cares about out of distribution. So what is out of distribution generalization? It means that the source distribution is different from the target distribution, or is different from the target distribution. And okay, sorry. So one interesting setting is the covariance shift setting. So what is covariance shift? It assumes that the input data distribution will change. However, the relation between the input and the target maintains invariant. Okay. And we have an example. So for example, we want to we have a classification problem, and in the source distribution, so in the training process we will collect data, and the data is often collected so from the outside, and in the test and in the test during the test case, so most picture will be is collected indoors. So for this problem, the input of the target distribution is different from that of the source distribution. Okay. And for the covariance shift problem, we have many interesting problems to study. For example, so what is the optimal algorithm for covariance shift? And since we often train the model by gradient descent or gradient descent with momentum, so what is the performance of ASGD under covariance shift? And when can SGD achieve optimality under covariance shift? Okay. And I will provide answers for these questions. So we still consider the linear regression. Okay, and let the matrix S be the source covariance matrix, and big T be the target covariance matrix. Okay, so in the covariance shift setting, so S and T is not the same, and we train the model by S and test the model using T. Okay. And okay, we still consider linear regression. And in covariance shift, so because the relation between the input and the output are the same, so it means that W star is always the same for the learning for the learning and testing, in the learning and testing process. Okay, W star is always the same. However, the measure becomes different in the covariance shift setting. So in the test process, so we care about the target access risk. Here, the risk is like W minus W star. Okay, in the matrix T norm. However, in the training process, okay, in the training process, we learn W by minimize W in matrix S norm. Okay. So we train in matrix S norm. However, we test in T norm, and S and T is different. S and T are different. Okay. Okay. And we first consider the problem. What is the min-max optimal algorithm for the coordinate shift problem? Okay. I only show the result. So the result is that so the optimal estimator is the standard least square estimator multiplied by a matrix A. So W height A is the optimal estimator. And how to obtain A? The A can be solved by a convex optimization in this. Okay. Okay. So the optimal algorithm is described as follows. First, we will solve an convex optimization problem like this, and then the optimal estimator is A multiplied the least square solution. Okay. Okay. And we can also establish from some lower bounds showing that so this estimator is optimal. Okay. But however, some researchers have already achieved this result. We later observed found it. Okay. We later found it. Okay. And then we can study the performance of stochastic gradient descent. Okay. So what is the performance of stochastic gradient descent? So as the solution of stochastic gradient descent can be considered as a special precondition of A. Okay, the optimal A should be the optimal A need to be solved by a convex optimization. However, for stochastic gradient descent, the A is like this. Okay, it's the top only the top is the top entry is 1. Okay, so because SGD only solve the top eigenvalue directions, and in the rest directions it will impose regularization and force the parameter to 0. Okay, so the solution of SGD can be considered as a special precondition on least square solution. Okay, so using this view, we can show that for many cases, the SGD is actually optimal. Okay, it's also optimal. So we propose a general condition like this. Okay. Okay. I don't want to introduce much details, and I only demonstrate some result. So we can show that when the density ratio of the target and source is bounded, then SGD is optimal. Okay, this is a very common setting in all the problems. Okay, and we can also show that if the KO distance between the source and the target is bounded, then SGD is also optimal. Okay. Okay. And we can also show some cases where momentum is probably more efficient than SGD. ASGD is more efficient than SGD. Okay. Okay. So we always in optimization, momentum is very important, and so in a line stochastic optimization, so for gradient descent, like for strongly convex and problem, like strongly convex problem, gradient descent can achieve 1 over L over mu complexity. Okay, and AGD can achieve square L over mu complexity. However, for most stochastic algorithm, so momentum is not that work. Okay, so for most in most analysis, SGD with momentum can only so the rate for SGD with momentum is 1 over square of t, and the momentum cannot accelerate this rate. Okay. However, for the linear regression problem, we can show that for some cases, and the momentum is probably work. It is probably work. Okay, more efficient than SGD. Okay, and then I will introduce our explanation for emergence. Okay. So the what is the emergence? So it describes that for example, with the increasing of training, and the model performance at initial is not very good. However, it becomes very good after some point. Okay. So after the training hits some point. Okay. So why it will happen? So I think the main reason is that we choose a different measure between the training and the testing. Okay. So if the target distribution demands high accuracy estimation in a localized region, then the emergence will occur. So for example, like in the left figure, okay, the target eigenvalue is in the black line, and the source eigenvalue is in the yellow line. Then if the first eigenvalue is large for the target, then the emergence will happen. Okay, shown in the right figure. So the risk will maintain invariant and then decrease after it hit some point. Okay. So no matter the algorithm, so you can use any algorithm. The performance is like this. Okay. So it is the min max rate. Okay. Okay. And then I will introduce algorithm for large language model training. Okay. In large language model training, so memory cost is also very important. Okay. So if we design an efficient optimizer that requires less memory, then we can enlarge the batch size, and so the algorithm will take less time to converge. Okay. So for the standard ADAM algorithm, so the optimizer memory is composed of two parts, so the first order momentum and the second order momentum. And in this work, I will consider reducing the first order momentum. Okay. Okay. So we first show our motivation. We still consider linear regression. So when we use the momentum, so because momentum can accelerate optimization, so when we use momentum, the algorithm's bias will be small. However, the momentum will increase the algorithm's variance. Okay, so for the problems where it has large variance and small bias, so momentum is redundant, and we can consider reduce it. Okay. And we also have some empirical studies. For example, so for the transformer architecture, so the embedding and the tension layers, so we can find that gradient is always sparse. Okay, and for the Q and the K block, we can find that the momentum have some block structure. Okay, some low rank structure like. Okay. So we need to study the heterogeneity of the blocks for the transformers. Okay, we consider the following partition. So for the embedding and attention output projection blocks, and we found we don't need momentum. Okay, and for the value layers, we require full momentum. And for QK and MLP blocks, we will propose a debiased low rank approximation of the momentum. Okay. Okay. So I will briefly introduce the debiased low rank momentum. Okay. So the momentum is actually not fully low rank. Okay. The eigenvalue or the singular value of the momentum matrix decrease very fast, and however, we can select out some top eigen directions. However, the rest eigen directions also affect the learning rate. Okay, so we cannot directly ignore it. We need to we want to design a debiased model to make the approximation is still full rank. Okay. And the okay, the debiased model is like okay, it's like this. Okay, so L and R are the low rank approximation of momentum. However, the momentum matrix is not low rank, and we will store RT, which is the gap between the momentum and is no rank approximation. Okay, and then we compensate the RT. Okay, compensate RT. This is the DeBios low rank estimator for the momentum. Okay. So our model can largely reduce the optimization memory. We can also use previous result to reduce the second order momentum. Okay, the algorithm named Adamini is a model to reduce the second order momentum, and our model is to reduce the first order momentum. Okay, so by combining the two models, we can have an algorithm named Adamini. Okay, this algorithm can reduce the optimizer memory by around 94%. Okay, and we can as we reduce the optimization memory, then we can use a large batch size, and the algorithm can train the large language model faster. Okay, and also we have comparison of the existing models. Okay, so from the iteration against the lost the picture. Okay, it describes the iteration against the loss. Then we can find that the performance of ADAMPT is nearly the same as ADAMW. Okay, is nearly the same as ADAMW. However, the performance of Galore, okay, the Galore is inferior than ADAMW. Okay, the Galore is the algorithm that directly use the low rank approximation to train the to reduce the memory. Okay, however, it's much I think it is much inferior than the standard ADAMW algorithm. Okay, however, and our algorithm has no performance degradation. Okay. And we also work on some fine-tuning task, and also the performance are very close to the to that trained by ADAMW. Okay. Okay, and thanks for everyone's listening. Okay. So if you have questions, so please ask me.
Sorry, can you please move to the slide where you define how you like decompose the momentum?
This page?
I don't know, with formulas, it was bound. With L and R. Yeah, okay, I see.
Okay. Yeah, the L and R are the no rank approximation of the momentum matrix. However, we will maybe you can see this page. Okay, then we will store a matrix called named as RT. So RT is the gap, okay, between MT and its low rank approximation.
Mm-hmm.
Okay, and we update using MTC. Okay, MTC is MT minus RT over some factor. So this factor is because the momentum, like we will accumulate the beta 1.
Yeah, okay, now I understand. But what happens if like you have like so what happens if MT is equal to LT RT?
Okay. Then RT is 0. Okay.
So RT is like a small one, yes?
Yeah.
So
The
okay,
LT and RT
sorry,
are the top
sorry.
eigenvalues. Okay, at the top eigendirections of MT. Okay, MT is not fully no rank, I think. It's okay. Okay. LT and RT are the top eigenvalues of
Yeah, okay, now I understand. Okay. And how you solve this arg minimum? You can solve it like, yeah.
By simple gradient descent, maybe by 5 step.
So you do some like inner optimization.
Yeah.
But don't you think you can solve it like analytically? So basically it's solved by SVD, yes?
No, the simple by gradient descent is okay. But
analytically it's solved by SVD.
Yeah, gradient descent, yeah.
Okay.
Alternative gradient descent or
how? Sorry?
Alternatively or just gradient descent for L, Rn in for L, Rn in parallel?
Using gradient descent to solve this. Okay. Like you have LT minus 1, like
okay, I understand. But and in practice, how many iterations?
around 5. And you can, because MT changes very slowly. Okay, you can at the next iteration you can initialization will you don't need random initialization. Okay, you can initialize LT and RT use the previous solutions. Okay.
And starting point previous L and R, yes?
Yeah.
And for V, no additional tricks with low rank.
Yeah. V is we don't use no rank. Yeah.
Yeah. Good, because we also have the same paper, but no, not the same, but all about memory efficient. Maybe you see Frugal paper, not the same idea. We use SVD and kind of decompose the parameters to kind of important, where we make Adam or SGD with momentum, and most of other parameters are not important, and we use just plain SGD or sin SGD as a cheap optimizer for most parameters. Yes. Okay. And yes, here quite nice idea.
I will read the paper. Okay, seems interesting.
Yeah. And we also look at your idea, because it's also nice. We think about this kind of make efficient in terms of the memory. Yes, and if it looks work nice in terms of the number of gradient descent iterations, it's quite a nice idea. Yes. Yeah. Maybe need to think a bit more, because yes, kind of combination of these two ideas, or just go to this direction is quite nice. Yes. Guys, maybe you have some questions to Professor Fang.
I think I have 2 questions. First question is about the application of clipping. I just want to ask Why do you choose clipping? Why do you need to apply clipping? Is it empirical observation or something theoretical?
No, just empirical. We found the maybe by adding clipping the performance is much better. Yeah.
Oh, okay, I see.
I think, yeah.
Yeah, thanks. And the second one is about the question of optimality. I would like to ask about maybe I'm not sure that it is possible to give me a simple answer on this question. Uh, I I don't fully understand how do we provide the optimality in this case, because as for me, the optimal rates in this regime, in this analysis, should be constructed, especially lower bounds should be constructed in a special way.
Yeah, the lower bound part is not designed by. We use techniques from statistical learning theory, not from optimization. Yeah, so this is a statistical problem. So given the number of data, so what is the best performance we can obtain? Okay, it's a statistical learning problem, and the lower bound is based on some techniques from information theory. Okay, it's not like the lower bounds in optimization. Okay, okay. It is not like lower bounds in optimization. We design some objective function that is very hard to solve. For this lower bounds, so it's a statistical learning problem, and the lower bound is obtained by techniques using information theory. So we give n data, and how can we? So what is the error between the optimal estimator we can obtain? Okay, between the ground truth.
Oh, if I'm not mistaken, you mean that the lower bound is constructed. As for me, they exist on they.
Yeah, like camera. Yeah, you know the camera inequality like this. Oh yeah.
Oh.
Yeah.
The lower bounds are constructed in information theory paradigm. Yeah, but I met a lot of papers with the lower bounds, but just a few of them are related with information theory, with the statistical lower bounds. Now I see these lower bounds are different from the classical ones, which constructed by the plane with the domain dimension or something like this. Yeah. Now I see. Now I see. Yeah. Thank you very much.
Yeah.
Sorry, I want to ask not a question, but maybe a suggestion. Can you please share the as I understand, these all are like your papers, or papers of your team. So can you please share them with us somehow?
Okay, I will text to the professor Alexandra. Okay.
Yeah. Okay, that's great.
And do you have this as a preprint or just plan to put to archive? Or...
Sorry?
Do you have this paper as a preprint with this low rank momentum?
Yeah, what paper are posted on archive? Yeah.
Yeah.
I can text it to professor. Yeah, to you. Yeah.
Yeah, guys, more questions? More?
I think I have no questions. I have
Yeah.
no more questions.
Okay. If no questions, let us say thank you to Professor Fang and also his students to participate in this seminar, to share this nice idea, quite close to our research. And maybe I don't say to most of our guys that we can collaborate with this nice group in these ideas or other ideas, and yes, can make a nice mutual research together. Okay, thank you very much, and
And
be in touch. Yes, yeah.
Yeah. Thanks for everyone's listening. Okay.
Yeah, thank you, and have a nice day. Yes.
Yeah. Have a nice day.
Yeah, have a nice day.